Let's look at a common example of the law of conservation of momentum as it is applied in many of the problems that you encounter in your physics books, in a physics text. And that's the problem with a cannon being fired. So here is the picture. We have a cannon, or at least trying to look like a cannon, and inside of it you see the projectile, the ball right there. And before the projectile is fired, the momentum of the system is zero. The ball is not moving, the cannon is not moving, nothing is moving. So mass, even though the system has mass, its velocity is zero. So the total momentum of the system is equal to 0 kilograms meters per second. After the ball is fired, here we are. After the ball is fired, you can see the ball is moving out of the cannon with some velocity. The mass times the mass of the ball times the velocity of the ball, let's say it's 10 units. So now you can see that objects are not moving, not stationary anymore. The ball is now booking it at a large speed, and let's say that this is the value of its momentum. The law of conservation of momentum tells us that if no outside forces are acting, and on this system there were no outside forces acting, the forces were applied inside of the cannon. There was no external force acting on it. So if the momentum of the system was 0 before, then it should stay constant. It should remain constant with no external forces acting on it. So now after the ball was fired, or after it came flying out of the cannon, we know that the momentum of the ball is not 0. It's 10 units. But the momentum of the whole system should remain to be equal to 0. So if the momentum of the ball is 10 units, then that applies then the momentum of the cannon itself, should be equal to -10. So the mass of the cannon times the velocity of the cannon should be equal to -10. And then the total momentum of the system, of course, the -10 plus the +10 is equal to 0, just as it was before. You've probably seen, or if you fired a projectile, if you fired a firearm before, you know that after the projectile is fired, there is a recoil. So after the cannon is fired, it doesn't remain stationary. It has a tendency, there's a force pushing it backwards, opposite the direction of the ball. And of course, if the mass of the cannon is much larger than the mass of the ball, that also implies that the velocity of the cannon going this way is going to be much smaller than the velocity of the bullet or of the cannonball, which is moving in that direction. So the cannon is not recoiling backwards with the same velocity with which the ball is moving in that direction. But how much velocity the cannon has after firing actually is determined by the ratio in the masses of the cannon and the bullet. So we could, for example, ask, if we knew the mass and the velocity of the bullet flying that way, and if we knew the mass of the cannon, we could find out how fast, with what velocity is the cannon moving in the opposite direction after the projectile is fired.